Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to find some insight into eigenvalues. Okay, well, what we said is an eigenvalue and an eigenvector are, it's a vector v that satisfies the equation that when you take the matrix times the eigenvector, the result is some scalar times the vector with which you started. And according to our last video, we found that if we solve the problem of the determinant of a minus lambda I equals 0, we find the eigenvalues lambda. So let's take a look at this. First off, we're going to let A be a 2x2 matrix as our basis for beginning our studies. So we'll just use the general form. A is the matrix of A, B, C, D. And let's see how we do this. Well, it says that the determinant of A minus lambda I. Okay, well, first off, we are going to have A. So here's the matrix. So let's do this. So A minus lambda I. This says I take the matrix A, that's A, B, C, D, minus lambda times the matrix I, which is 1, 0, 0, 1. And remember that means that this lambda multiplies every component inside that matrix. So it's lambda times 0 even. So let's just write this so we can see this is A, B, C, D. Minus, well, lambda times 1 is lambda. Lambda times 0, that's 0. And lambda times 0 again, 0. And lambda times 1, lambda. Okay, and now let's subtract these. So this becomes A minus lambda, and a C below it, and then we have a B, and then a D minus lambda. And there we have it. That's A minus lambda I. Okay, but what we said is the determinant is 0. So let's find the determinant of A minus lambda I. Okay, so I'm just using that down below. That's going to be A minus lambda times D minus lambda minus, and then the anti-diagonal, that's B times C, minus B times C. Now and this equals 0. Okay, so now let's see. I'm going to distribute this, and I'm going to distribute, we'll just distribute it starting with the A. So A times D is AD, A minus A lambda, and then I'm going to have a minus D lambda, and then plus a lambda squared minus BC equals 0. Now let's do this on purpose. I'm going to rewrite this by decreasing orders of the variables. So we'll put our lambda squared first, our lambdas next, and our constant. If I do that, I'm going to have a lambda squared, and then I'm going to have a minus A lambda minus D lambda plus AD minus BC equals 0. Now let's do one more step. Let's factor our lambda out of the second and third term. So this becomes a lambda squared minus A plus D times lambda plus A times D minus B times C equals 0. Now look at this. This is absolutely fascinating. This is a lambda squared. I'm going to come back to this middle term, but A times D minus BC, you should probably say that out loud now that I just pointed it out. Sure, that's the determinant of A. That's the determinant of the matrix of A equals 0. And look at that, A plus D, A plus D. Well, if you have a pretty pink color, you'll be able to see this. A plus D, that just is the addition of the elements of the diagonal of the matrix A. And that has a name. The sum of the diagonal of the matrix is called the trace. So in other words, this becomes minus the trace, and we abbreviate it with a TR, the trace of A. So let's put over here TRA means the trace of A, and is the sum of the diagonal components. Diagonal components. Oh, wow. So, in other words, that's it. That's the pattern every single time. Now, if you forget or you don't believe that it's always going to work, that's fine. Just go through this exact same process. Just repeat this process that we did right up here in our opening move of just distributing and taking the determinant, distributing, and then rearranging and collecting like terms. But I want to pause here for a moment, because remember there's something else that we said about this polynomial. All right, and let's actually go to a second page for this. What I want to do is we have that lambda squared minus the trace of A times lambda plus the determinant of A equals 0. And remember, the general form of this is when A is 1, we said this is lambda squared plus B times lambda plus C equals 0. And actually we were using S's, but it's the same problem now. And what we also said is if our solutions were lambda 1 and lambda 2 are solutions, remember what we said. One of the relations we found was that lambda 1 plus lambda 2, the sum of the solutions, is equal to minus the B term. Well, I can also write this as B is equal to minus lambda 1 plus lambda 2 but look at this. What else is the B term? But the B term, well, this is also equal to minus the trace of A. But this means then that, so this implies then that lambda 1 plus lambda 2 is equal to the trace of A. That's our first check that we have. The other check we said is that the product of the solution, so lambda 1 times lambda 2, is equal to the value of C. But wait a minute, in this case, C is the same as the determinant of A. So in other words, another check is that lambda 1 times lambda 2 equals determinant of A. I hope that helps, and thanks for watching.